Let's talk about centripetal motion. We've derived centripetal acceleration in a previous video, but the concept here is that if we think about Newton's second law, so the force is directly proportional to the acceleration, and acceleration is, well, basically the time derivative of velocity. So we're looking at this relationship here. So if the total force, this is the total force on an object. So if the total force is 0, then the change in velocity is 0. In essence, so an object will maintain a constant velocity unless there's a net outside force acting on it. And a constant velocity would mean that, so if the total force is 0, then the change in velocity is 0. In essence, velocity is constant. Since velocity is speed in a particular direction, that means that an object wants to travel at a constant speed in a constant direction. The tendency of an object to want to do this is called inertia. So constant speed, constant direction. So if something is not traveling in a constant direction, then there must be some outside force causing it to change. And so if I take an object and I attach it to a string and I start slinging it around, that object wants to travel in a straight line, assuming I'm rotating it about like that. It wants to travel in a straight line, and if I let go, it is going to travel in a straight line. Potentially, it might go downwards because of the pull of gravity. But the fact that I have it traveling in a circle means that the direction is changing, which means there must be some force acting on it, which means there must be an acceleration. We've dealt primarily with acceleration because of change in speed, but there's also acceleration because of change in direction. So the force that causes this thing to go in a circle is a force that is pulled inwards like that, and therefore I believe it's the Greek for center seeking, it is called a centripetal force, which is related to centripetal acceleration. From the earlier derivation for it, centripetal acceleration, the magnitude is the speed squared over r, or omega squared r, depending upon what you're looking at. So it is a centripetal force that is pulling it inwards. So if you have something traveling in a circle, there must be some force causing it to do that, as was just said. And when I plug into Newton's second law to get my equations of motion, that acceleration is centripetal. So for example, why don't we just take the simple example of I have a table here on the floor, there's a hole in the middle of the table, and I have from a side view, I have a mass that's going to basically be going around in a circle on the table. So from an overhead view, this is overhead, side. I'll have a mass that is traveling in a circle here attached to a string, and the string is attached to a mass down here. I'm going to call this mass 1 and mass 2. If I do a force diagram for mass 1, I have weight acting down, weight 1, I have normal force acting up, and I have a tension pulling in towards the middle. I'm looking at it when it's here. Obviously, as this thing moves around, the direction of the tension is it's constantly towards the center, constantly pointing towards the center. Just that I'm capturing this moment right there. If I look at mass 2, I have weight 2 acting down. I have tension acting up. And if we assume ideal situation here, I am making this a frictionless table, that those tensions will be the same, a nice ideal rope. So when I do my equations of motion for this one, well, my acceleration is that direction. Here, there is no acceleration, so it doesn't really matter which way I make positive, so I'm just going to make up positive. You know what? I am going to make down positive. I'm going to make the math just slightly simpler. It'll save us about 3 seconds. So in this case, I'm going to set my coordinate system like this. I have I1 hat, J1 hat, and then here I'm going to make this, I could just keep it as a positive because it's one-dimensional right here, so I can get away with just plus, but let's just go ahead and make it slightly more formal. I'm going to call it I2. Now, one of the reasons why I chose it downwards is that if I follow the string here, I have tension pulling this way, in the positive direction, and it may as well keep the same overall direction along the string, the positive. So to the left is positive and down is positive. So now when I set my equations of motion, well, working through the process, force diagram, acceleration, coordinate axis, we've done that. Nothing to decompose because everything is in the positive or negative hat direction. So that's in the positive I hat, positive j hat, negative j hat, positive I2 hat, negative I2 hat. Equations of motion, I'm plugging in F equals ma. I'm going to have three equations, two from this and one from that. So I have y minus w1 is equal to 0 because there's no acceleration vertically here. We have tension is equal to mass 1 times centripetal acceleration. So this is my J1 equation, my I1 equation. And then my I2 equation is, I said down was positive, so I have W2 minus FT is equal to 0. I don't know if I stated this before. This thing is traveling around in a circle, and mass 2 is just hanging there. It's providing the tension to allow this thing to travel in a circle. Very similar to the Centripetal Force lab. So substitution comes next. And so I have a formula for weight, and I have a formula for acceleration here because of the centripetal acceleration. So this becomes y, and then bringing it over, equals m1g. Ft is equal to m1 v squared over r, or m1 omega squared r, depending upon what is actually being asked for here. And I guess I haven't stated that. We're just sort of exploring at the moment. And over here, we have m2g equals tension, or m2g minus tension equals 0. We'll just keep it like in that form right there. So now, let's find the speed. So given these equations, I'm going to add these together. The tension is going to disappear because I have positive tension here, negative tension here, and that's what I was saying of the reason of choosing the axes the way I did, or a coordinate system for each as I did, is that the tensions would disappear. And so I'm left with m2g is equal to m1 v squared over r. And so v becomes the square root of m2gr over m1. And this is just a basic centripetal force problem. Let's take it to the next step. Suppose I'm swinging a mass around, and I've got a string here going through a tube attached to some mass 2 here, and I have this as mass 1. Slightly more complicated because this is traveling in a circle right here. I will know this length, so this directly relates to the lab. I know that length right there. From here to here, I will know mass 2, and officially I'll know mass 1. However, we're not going to use that in order to solve for mass 1. We're going to pull that from a graph. But the radius, well, we'll get to it. So our force diagram, so for M2, I have tension pulling this way, and I have its weight acting down. So M1G. And for M2, similar to the problem I just did, I have M2G acting down, and I have tension acting up. This is just weight 1 and weight 2. I went ahead and did the substitution at this point. If you don't like to do substitution yet, do it later. Set up my coordinate system. I know that this is accelerating in that direction. It accelerates towards the center. I'm capturing this at this point in the circle. So I set up my coordinate system like this. I'm going to call this I1 hat and J1 hat. And over here, I'll make this I2 hat, very similar to what I just did. So now that is the only force I need to break up here. I think in the lab, that's the angle we're talking about. That's the angle I at least identify as theta. So that's this angle here. Two parallel lines cut by a transverse. Alternate interior angles are congruent. So this angle here is theta. And so when I break it up, I got my mass 2 here. I've got W1 or M1G acting down. I have Ft cosine theta acting to the right. Ft sine theta acting up. So now when I do my equations of motion, I have Ft cosine theta is equal to m1a sub c. It is my centripetal acceleration. And again, well, we'll get to the r in just a second. And then I have Ft sine theta minus m1g equals 0. Over here, I have m2g minus Ft equals 0, because as this is swinging around, you want this mass to basically stay right where it is. So now, well, ultimately, I want in the graph, I'm plotting omega squared versus tension. So why don't we go with that? From this, I know what tension is. Tension is equal to m2g. Looking at these equations right here, when we do substitution, I have Ft cosine theta is equal to m1. And because I'm plotting omega squared, and this is something as you read the lab, you will see, this becomes m1 omega squared r. And then I have Ft sine theta equals m1g and m2g. And Ft equals m2g. Now, it looks like I've got this cosine in here, and that potentially makes the plot a little bit tricky, except we actually have a little bit of information here, and one of the reasons why omega squared is much more convenient than v squared in plotting this, even though there is a version of this lab where you plot v squared versus tension. If you look at the physical triangle that we have here, physically that triangle right there, that is a right angle, because this mass should be traveling in a horizontal circle, and this is relative to the horizontal. So I have, this is length L, that's R, and that's right angle, this angle is theta. So we have a relationship between R and L. I know that R divided by L would just be the cosine of theta. This is the adjacent over the hypotenuse. In other words, R is just L cosine theta. And this allows us, when we make that substitution in for R, this gives us the tension cosine theta is equal to m1 omega squared L cosine theta. The cosine thetas go away, thank goodness, because keeping them in there is a real nuisance, which would have happened if we had the v squared over r. It becomes a mess. So now, if I'm plotting omega squared versus tension, well, as typical, I want to get it into y equals slope x plus b form, in other words, slope-intercept form. I need to have omega squared is equal to something times my tension plus something. Well, this is what I'm working with here. Solve for omega squared. Omega squared is equal to tension over m1L. In other words, this is 1 over m1L times the tension plus 0. So there's my slope. And then once I have my slope, L I will know already. We can now calculate m1 and then compare it to the actual value.